All right, welcome everyone to another OCP Tab call. This is call number 123. Today we have Med Belhadj. So Med has 30 years of experience in hardware and system design for various telecom and datacom networks. Previous companies include Cisco, ST Micro, and Nortel. Current focus of Med is on precise timing applications for data centers and telecom networks. Med has a PhD from University of Rennes from France. And today's topic is about time sync for congestion control. And this will be like the part one. And I think you have all the parts in one session, right? Or there will be subsequent ones, Med.
No, second part would be in
Yeah.
another talk. Yeah.
Yeah, so then there will be a sequel. So this one will be basically about the survey of current algorithms. And with no further ado, Med, the floor is yours.
Ahmad, could I interrupt, be a little rude?
Yes.
I just want to mention that this is also a joint presentation with the IEEE Industry Connection on Timing. So it's officially part of that as well.
Yes.
With that said, please, Med. Thanks.
Thanks, Rodney. Thanks very much. Thanks, Ahmed. Hello, everyone. So as both Ahmed and Rodney was mentioning, this is part of an effort for our group to kind of look at application of precise time sync for congestion control and answer kind of a few questions. So kind of maybe the reason I kind of volunteered for this as Dan and Hisham were basically spearheading the work stream number 10, looking for this kind of application. My background was I've done some fairness algorithm for RPR for people who know 802.17 and dynamic bandwidth allocation. So those two use basically very short control loops, so they're pretty fast. And given the tendency of what's going on in the data center, I thought this would be a very good a place to contribute. So what I'd like to kind of, for the group to kind of get out of this, especially this first part, is kind of get the lay of the land, as what's going on, where the direction of the kind of current work is going, and how could we best as a group for time and synchronization approach kind of adding real value in this. The next step, I have to say that I was a little bit taken aback at the volume of work that's being done over the last little bit. I was pretty familiar with things a few years back, but if you look at, I just took a sample or a snapshot of what happened since the inception, and I started that at the TCP paper that had congestion control for TCP, which was published in 1988. And you can see there's just like 10 years of not much happening, but then you got 20 years with almost 1,000 paper a year. So a couple of things here is like, why is this such a hot topic and why it keeps being kind of a highly active field? A couple of things you could see, probably it's familiar to a lot of you, but it bears repeating. It's a system level problem. So you could basically congestion, we typically associated with transport protocol, but it actually could come from lower layer, link layer and network layer, etc. have also their own congestion and applications. So if you're doing streaming, of course, video codecs adjust based on the congestion. So it is something that is happening at multiple levels, which makes it complex. And of course, the second part of the equation is that things keeps changing. So TCP was very adequate with the way it was at the beginning, but once you start using basically satellite for it and data centers with high bandwidth and low latency, what used to work before was no longer useful. So the talk is like, for this is kind of 4 pieces. First one is just a quick background, and please let me know if everyone is familiar with this. I can skip it pretty quick. But just a link layer, so some of the basics of what the lower layer from the transport layer that is most relevant to us. And then the second part would be kind of going and looking at what's going on in the transport layer, where we are right now, and the kind of the trends of where things are going. And with the third focus on basically the timing portion of it. So, what timing is already used in some congestion. So how is it used, and what are the protocols that use it? And of course, the next step, which is basically just kind of a prelude to what we will be looking at for the next part, or the sequel of this, which is basically kind of finding some good applications and good uses for precise signal. So network layer, just kind of quickly go over some of the concept. Flow control, ECN, packet trimming, network telemetry, and signaling, and credit-based. So Ethernet flow control is kind of, people who are familiar with RDMA over converged Ethernet, is used for simple back pressure. The old Ethernet just used simple pause. You pause traffic, and the sender, so a sender stops sending packets. The kind of wrinkle that was added with priority is just you use multiple priorities, and instead of stopping everything, you stop at given priority. There is an excellent paper that a team from Alibaba and Microsoft looked at some of the issues when deploying Ethernet PFCs at large scale, where they had in terms of PFC storms and deadlocks. You can kind of intuitively think that if you back pressuring, even if it is based on a priority, if there is another, it's kind of indiscriminate. So if you have another flow that has nothing to do with the congestion, it'll still be stopped. So most of the algorithm that you see there will basically kind of use it as a last resort. So hopefully it will not kick in unless you have you kind of did a bad thing at the higher level. There is a project for people who are interested that is an improvement over basically PFC, which is source flow control, which is an IEEE 802.1q DW, and it basically kind of refine the signaling back to the source and uses it in a more discriminate fashion. Next one is ECN. ECN was quite useful for people who are familiar with the data center TCP. So typically packets in a switch or a router will get dropped, but if the queue reaches a certain threshold, but there is a active queue management where instead of basically dropping packets, what you do, you'll see you can see it on the image on the right. Instead of basically just dropping the packet, you mark it. There is a bit in the IP. There are other layers that also could have notifications like that. And instead of just dropping the packet, you mark it so the source has an indication about this. So is this common knowledge for everyone? Is the group would like me to continue with this, or we can skip to the transport?
You can continue. I like it.
Okay. So packet trimming is if you kind of have different layers in terms of signaling back to the source to kind of have it reduce its rate or handle the congestion. One extreme is basically you just drop the packet and wait for it to time out, and it realizes that it needs to reduce its rate. The indication you mark it in the packet is the next best thing. And packet trimming is actually where when you get to a point where you have to drop, instead of dropping the whole packet, you just chop it off, keep the header, and the end device will be able to notify the sender, and you basically have a better signal back to the source. Now it needs support from the switch to actually implement the trimming logic. Now there is kind of work that is being done in terms of trimming for application like machine learning, where people are looking into basically positioning some of the most significant bits in the front of the packet. So when you trim it, you actually don't just deliver the header, you deliver a minimum amount of quote unquote useful. The definition of useful varies, but those are some of the techniques to kind of refine the signaling back to the source for the lower layer. Network telemetry and signaling. This is basically what kind of, if you wish, the next level up again from in terms of feeding back information to the source so it can do a better job. You can think of basically this as a control problem. You have some information that get fed back to the source that does a computation. You have a time constant that is like how many times you're sampling your system and adjusting your rates. The telemetry allows you to basically get a much richer signal or information about the congestion status of various nodes in your path from the sender to the receiver. Of course, like with everything, there is tons of different standards. Some of them, like INT, coming from P4, it's programming, the data path programming language. I'm sure quite a few of you are familiar with that. It requires, of course, a switch and a host support. And there's few challenges with tunneling and if that information is available to everything in the data center. Certain congestion control that one of them will look at in a little bit more detail later on, which is HPCC. So those are basically, they take the INT's information quite to kind of feed into the argument. There is the kind of the flip side of the coin is just credit based. This one, I'm not going to spend too much time on it. It's if you're looking into comparing things with InfiniBand, or it's what's used for PCIe or CXL, and basically instead of be it sender driven, it's receiver driven. You give credits and you kind of avoid having drops because the sender is not allowed to basically overflow whatever number of credits you have. Transport protocol. So we talked about the lower layer. Like now, if you kind of go into the lay of the land in terms of transport protocol, here I picked two which are the most common one, which is TCP and RDMA over Rocky, which would be of interest to the group here. So I put a small diagram here that kind of shows the kind of what the traditional TCP looks like. So it's everyone, I'm pretty sure, is familiar with this, but a couple of the concept that you want to keep an eye on is this additive increase, multiplicative decrease. So intuitively, what it means is that you basically start ramping up slowly till you reach a point where the original TCP handle what it had as an indication is packet drops. When you reach packet drops, you back off, and the back off is multiplicative, so it's much sharper. Now, this worked well in the early days, but as you can probably guess, this is not ideal at all. So there has been quite a few refinements since. So kind of if you wanted to go and look at kind of what the field looks like in terms of congestion control, you have basically concepts that I think just they're saying here or putting it in an organized fashion. So you have avoidance, which is scheduling or pacing. Some algorithms basically send packets at a specific rate. Control and recovery. So whatever you do, at some point there might be a congestion. So the ability to kind of recover from congestion collapse has to be built into whatever algorithm you do. Detection and signaling, we talked about that quite a few times with different layers, signaling, etc., and how rich that signaling and accurate it is. One aspect that actually is quite lacking, there's a few groups that actually looked at that, but characterization and diagnostics seems to kind of not have been a very well addressed part here. Design trade-off is like typical stuff. So you have distributed versus centralized. Most of the algorithms are distributed, very few are centralized. Host driven, so either the sender, the receiver, switch, or hybrid. The type of control or avoidance, is the algorithm aggressive, or is it more of a passive, kind of conservative way of claiming bandwidth? And of course, what layer or combination of layers it uses to kind of handle congestion. The design criteria, or if you want to look at the optimization, what are you trying to get at is throughput or good bit utilization, delay, and especially for DC, you want to talk about tail latency, fairness, you're sharing a bandwidth between multiple flows and multiple users, and of course stability and conversions. But that's a kind of tricky balance, because you want something stable, but you could have something stable by making things very incremental, but also you need conversions at a fast rate. There's a lot of stuff in the data center that's happening at quite a fast pace. So you want to be able to do that. So I put a few slides for anyone who is interested in kind of diving into this in a little more detail in the back. But if you kind of look at bird's eye view of TCP, the TCP, Tahoe, Reno, etc. This is kind of the classic ones. TCP cubic is what very likely runs on your computer, and there is the delay based are the ones that are of most interest to us. But you can see here the DC TCP is ECN based. And there's a few new ones that are not included in this survey, but in other surveys. There's about, I had to stop at 25, but there's 25 surveys on TCP congestion in various environments. So there's for multipath TCP, and of course, there's kind of various algorithms that were done through ML. The next thing, so cubic, as I mentioned, is one of the most used algorithm out there, and we talked about the additive increase, multiplicative decrease. So what this algorithm did was basically have a way of remembering what your last window was, and it reaches that window very quickly, get back to where you were, flatten a bit, and then try to claim new bandwidth if it's there. It's been in use for quite a while and has proven to be a pretty robust robust algorithm. DC QCN is, for people who are familiar with RDMA over converged Ethernet, RoCE, is basically the default algorithm. Everyone picks on DC QCN, so if you look at some of the comparisons there, it is a good protocol. However, it suffers from a few issues. So it is based on ECN, so marking at the lower layer. RoCE v2 is basically RDMA over UDP over IP, so it uses ECN marking, and it uses, of course, for lossless Ethernet, it uses BFC to guarantee that Ethernet is not going to drop packets, and it sends congestion notification packets back to the sender. One of the major issues about it is basically it requires almost 15 parameters to tune. So there is a couple of papers, if you're interested, that talk about all the issues for large-scale deployment, one of them from Meta, and one of them from Alibaba. And as with pretty much every algorithm you see there, there's like variation and improvement and slicing and dicing. So it's quite a rich field, and there is a lot of variation and improvement over time. Next is HPCC. So this is where I put the reference on the right there. So this is an algorithm that basically kind of try to kind of address some of the issues with DCQCN. And the interesting part of it is it has a heavy use of, it presupposes that you have in-network telemetry, and uses 3 parameters instead of 15. And basically it relies on a very fine-grained information about rates, delays, timestamps, etc., from the switches. There is an IETF RFC for it, and there is actually one that was uploaded January 5th for HPC++. Again, like every other algorithm, there's numerous modification and improvements, some of them large, some of them very small. But it is an actively developed algorithm. I put here a couple of algorithms as well that are interesting, and one of them is RCC, which is a receiver-based. So, kind of, hopefully you recall that when we talked about credit-based in a lower layer where you kind of send back credit, this comes from basically an observation or some work that I think Google had a couple of papers where they described that the majority of the congestion is happening at the kind of at the exit point, basically the last hop at the top of the rack switches. So what this does is basically, because the link is only between a host and the top of the rack, you kind of concentrate on doing that. The other one is basically a combination, of course, so it looks at what it calls exclusive is the link between the host and the top of the rack. And then basically the rest of the network, which is the switch in between either the receiver or sender, you kind of use classic sender-based program. So that's the kind of the typical, or the what you would see if you were to look at the various transport methods. Here I put a quick protocol from Google. So they put it as a replacement for HTTP over TLS and TCP, and it's quite, for a newer protocol, it has quite a bit of traction and use. One thing that I'd like to kind of, maybe it's obvious to a lot of people, but one thing, it has a use of congestion control, but the thing that I want to kind of highlight here, it has an excellent design rationale for, I put the reference there, multiplex stream. So when you're trying to build a new transport protocol, so we talked about layer 2 and layer 3, let's say we build in this new thing which has timing on it, etc. One thing is like if I'm doing a new protocol, like Chroma, for example, did, you would go and change a protocol number and put it on IPv4 or IPv6. But that is not a very practical way to do it. If you look at almost all the new transport protocols, be it Ultra Ethernet, TCP, they all use UDP as a stack. And there's a few reasons for it. And that paper goes into a lot of gory details. If you're interested, I strongly encourage you to go and look at it. But put a quick summary here. Of course, UDP is so lightweight, it's really IP with a source port and a destination port. Middle boxes are pretty tricky to kind of, if you want any kind of realistic deployment, middle boxes are like things like firewalls and load balancers, etc. Anything that they don't understand, they think it's a security risk, so they drop it. And you would think that, oh, okay, well, after updates, I can do that. Apparently, it's not that easy. So the paper goes in detail in terms of their statistic and what they measure it in terms of how hard it is to deploy a new quote-unquote transport mechanism. So pretty much everyone goes and puts whatever you need to do and put it on UDP. It's supported by the kernel. You have things like kernel bypass, zero copy, etc. And like TCP, so if you found really a nice algorithm to improve TCP, you need to put it in the kernel. This it's like a user application space, so deploying it, changing it, etc. is not a big deal. Preventing ossification, so that was also another important thing, is that if you have it now part of the application, so basically experimenting, extending it, updating the protocol becomes very easy. The third layer of it, which is also interesting, and it's going to be interesting to this group, is that you can actually, because it's a simplified algorithm, you can do a lot of things in a DPU or smart NIC. So if you want to have hardware offload, which basically most of the RDMA over RoCE or whatnot, they all use some form or another of hardware acceleration. One other thing that also bears kind of noticing is the kind of widespread acceptance of distributed switch fabric. So Cisco, Juniper, Broadcom, Ramon, and others. So kind of more or less the same structure is you basically have two layers and addressing issues with the existing network. It targets mostly backend networks where used for HPC or machine learning. And instead of basically relying on typical networking algorithm, use what is used for switch fabric. So basically you're pushing the decision of spraying the packet and reordering them into the switches rather than, so the hardware is going to do all that. And same thing for the congestion for the management. If you're building a router with multiple shelves, you'll have to distribute the switch fabric anyway. So the same techniques that are used there are used in these kind of deployment. So the end result, it's not like you no longer have congestion, is that the congestion is pushed to the last hop, which basically connects to the to either the host or the top of the rack, from the top of the rack to the host. Of course, Ultra Ethernet is an effort to basically standardize parts of this type of architecture, and currently it's standardizing two options for congestion management. One is sender and one is receiver driven. Any questions? I covered a lot of stuff, so I'm not sure if people have any questions here. I'll pause for a minute.
I think it's been pretty good.
Excellent.
There were some issues with voice quality, so I might be just try and speak a little louder sometimes.
Sorry.
Yeah.
Is it better?
Yeah. No. It's just every now and then it goes low or something like that. But yeah, so far so good.
Excellent. Time delay base. So one thing that kind of, when you look at kind of the various congestion control, when we talk about time base, or if as a group, if we want to get into kind of suggesting some algorithms or solutions for this space, we're talking about one-way delay. RTT doesn't benefit as much from precise synchronization. So there's a couple of, there's a lot of algorithms. I think in the slide that I showed previously that showed all the delay-based algorithms. There is a couple of algorithms that are kind of interest. The first one I'd like to talk about is Belhadj, which is the low extra delay background transport. If you have a Mac, it's running the OS updates, and basically it's kind of less than best effort. And what it's a fairly simple, not simple, but the concept is pretty simple. It's get out of the way if there's other traffic. So it's used for peer-to-peer networks and software updates. One thing that is interesting about it is that it uses one-way delay, and one-way delay with kind of a very simplistic, or not simplistic, but kind of rough. It doesn't use tight synchronization between nodes, but at this scale, because it's talking about doing background traffic at large distances for like software update or peer-to-peer traffic, we're talking hundreds of milliseconds. So really, even though it has a lot of challenges with estimating the one-way delay, it's good enough. So it starts at it's rough and coarse, but even with clock drift and route change, and it has some mechanism in it. Of course, it has the original Belhadj had some kind of issues, as pretty much every algorithm. You could see that there is a progression where people, as it gets deployed, get refined and a few things added to it. It had a latecomer advantage. Of course, it gets out of the way, but just so happen if there's another Belhadj, it actually kicks the first one out. And so there were multiple evolution to that protocol, like Belhadj++, etc. And they did a few tweaks to the original algorithm to make it better. Next one to talk about is Swift. So if you think of Belhadj as like talking about the millisecond scale, Swift is the microsecond scale. So for example, it is one of the options used for the Google Falcon transport. If we want to basically kind of map the progression, we'll start with millisecond. This is microsecond. what we're aiming for is going to the nanosecond. So Swift is kind of the closest to what we want to get to. It's still, if you look at some of the implementation details, timestamps are resolution of about 130 nanoseconds. So really, as we talk about precise timing, it uses really good timing, but it's not precise to that level. So few advantages of Swift. It's based. I put here a reference to the kind of the main path. So it uses, number one, it uses actually hardware timestamp. The majority of the other ones, when you're talking about calculating RTT or whatnot, you're just getting system time. So we're not talking at PHC or PTP time from getting it from a NIC or from a device that supports accurate time. So it gets the timestamp as close to the hardware as possible. Now, the nice thing about using delays is that if both ends of the link are synchronized to within a reasonable amount, in this case, Swift is in the hundreds of nanoseconds to the microsecond, you get a fairly good view of the delays, so the residence delays through the switch. And the nice property about it is that it doesn't actually presuppose any kind of support. It doesn't preclude it either otherwise, but if you have support and you can have a finer grain of telemetry from the switch, even better. But it's the nice thing about it is that you're not dependent on a very specific type of deployment. So it can be a lot more flexible, but if more accurate information or hardware support is available, you can make use of it. So for anyone who is interested in, as I mentioned, this is like an open call. I know Dan and Hisham would be really happy if other people would like to kind of chime in or contribute. Or so there is a very good discussion in the 3 papers I put at the bottom there: Swift, ECN, or delay, and a principal look at the utility of feedback and congestion control. So this is kind of a rebuttal and a rebuttal of the rebuttal. It's quite interesting to actually read the detail. When I was preparing this, initially I was thinking I could take this and basically go through the gory details, but I decided against it. And I was like, I rather kind of present it so folks kind of get a good idea of what's going on across the field. And probably in part 2, when we get to doing a couple of alternatives or proposals for a more detailed one, we can go into the nitty-gritty details and basically trade it off the various knobs. But if you're interested in it's something that you'd like to look at, it's those 3 references are excellent in terms of, and from people who are looking at things from different perspectives. So if we want to go and say use precise timing for this, we have to basically get where the pushback is coming from and have a very good answer to those questions. And so, well, there's a lot of people who have very valid criticism for some of the kind of delay-based mechanism. And if you want to basically propose something like that, those concerns have to be addressed. Next step.
Med, could I ask? So I've never heard of Swift myself. I could go and learn more about it, but just at a kind of a high level, when it says NIC timestamps, so if they're using system time, that's usually NTP, and that has whatever accuracy it has. when they say NIC timestamps, I guess I'm a little
Well,
confused by what they mean by that. I mean, that's
well,
not
they read-
synchronized time. So the timestamp from one NIC has no relationship to the timestamp in another NIC. They're not. You can't use that to any. I guess I'm a little lost by what they mean by NIC timestamp.
Oh, so what they mean by it, so, sorry, Rodney, just to clarify, they use literally a PHC read. So I know that because they kind of basically say that it takes 2.4% of the algorithm to read the timestamp. So they do synchronize them.
Oh, okay. So the protocol has its own,
Correct.
non-PTP mechanism for synchronization. Okay.
Correct. So
okay.
So it is built on, so so think of it as like the lead bat is like, we'll use sys time and we will use one-way delay, and it's really rough, but we don't care because we're dealing with things, quantities in the hundreds of milliseconds.
Okay. I
Swift
got
takes
you.
it another layer. It says we need PTP, we need hardware timestamp, and when I timestamp a packet that is leaving, I'm not using. If I use sys, it has to be linked to the.
It has to be linked to the PHC stuff. Okay,
correct,
gotcha.
Correct. Sorry, I did, but I will. So
no, that's high level enough. I realize you were trying to keep it high level, so I get it. No, thanks.
Well, with the time allocated, I was like, okay, you can't go in between. You either choose to kind of basically give a global view or take one and just like go down to the implementation detail.
I gotcha. Yeah. I'm not asking you to go into too much detail, but I understand what you're saying now. I got it. Thanks.
But for the next one, I certainly will.
Hey, by the way, it's an interesting point because this you're looking at your list there. Many of those use timestamps, and the problem I had was when I was going down this path of this tree, was that we were trying to do multicast, and so it turned out to be a real issue, real problem. So to Rodney's point, so these are all flow-based timestamps. So here,
correct. Yeah. And the other thing as well that is like, the other point is there is a difference between what the PHC or whatever implementation of PTP you do to synchronize the clock, but also the algorithm itself. Like it would be like you take the timestamp, and if the timestamp counter gives you a quantity in say nanosecond or even better precision, but they kind of drop off the lower 8 bits or 7 bits or whatever it is and don't even use it because they're not concerned about granularity to that level. And that's a very important point, is if we're trying to basically improve things and say you need that precision, we have to give a good rationale of why that precision is needed. So it has to basically improve these type of algorithm to a point where you go like, okay, don't lose those bits. And of course, the other question is, we need all the nodes to be synchronized to within that precision that we want.
good point.
Any other questions?
Just to clarify one, following up on Rodney's comments. So for the protocols that are using the hardware timestamps and the NICs themselves, are they assuming they are relatively well synced either to the same grandmasters or to reliable sources? Or did these fall apart if one of them is synced, let's say, far off from UTC?
Correct.
Gotcha.
So, and that's the other thing as well, is like, I know we had this conversation before, is like, for something like this, it might actually be an important point to basically look if there is a good reason to do precise timing at that level, and we can show really great performance with precision of X. For this this one, there's really no reason to even try to sync it to UTC, where if everything is within the same administrative domain, we can have an arbitrary time. And as long as all the nodes are synchronized, if we can synchronize them to within a certain precision, the fact that they follow UTC or not is completely irrelevant. We are concerned about the details and how they view time between each other, not what the rest of the world sees it. Okay. Next step. So kind of from the discussion we've had over this, one thing that kind of, if you, at least that's kind of my feel in terms of what, looking at what was going on in terms of the trends, and maybe some of you have a different take on it, but it seems like it's not like there is the silver bullet, or you're going to have one type of congestion control. Seems like a lot of different application and deployment scenarios are going and rolling their own. The second part of it is like, it looks like the path to roll your own is pretty clear, and a lot of people are taking it. So people are deploying stuff over. You even have a template. You can start with doing a software only thing over UDP, and then moving it into a smart NIC, and with the network support, etc. So the kind of the sequence of events that you can do to deploy something like that is kind of fairly established. However, the thing that I think, David, that there is a group in your university that did some good work on diagnostic and monitoring for HPC application, but I don't know if they're still active in that domain or not.
The rule is, if it's silent and it's a question, the answer is yes.
Okay.
No. Full disclosure, I'm not sure, honestly, because I'm based in downtown Chicago, so I interact very, very little with the people down in Urbana.
Oh, okay. I thought maybe. Yeah. So I mean, kind of, I don't think you know, the work they did was really great. They did it for a specific application, but one thing that I thought would be a good avenue for the group to kind of look at is this diagnostic thing, because if my hunch is correct, and it might not be, but and we're going to have a lot of different applications riding on UDP, doing their own congestion. Sure, in some cases with backend network, you might have like some controlled application. There'll be only few or one or whatnot, but these applications will change and things will kind of get messy. And it doesn't seem like there is a lot of, so far, there's a lot of ways of actually quantifying and characterizing how good or how bad. Even when you look at comparison between the various congestion control. So when I was reading some of these papers, they only have snapshot at certain times and certain implementation. And when you look at the issues of deploying something in the kernel or monitoring, you know, even a lab setup, it becomes quite a difficult thing to do. So I think something like you know, delays which do not require a lot of support from the hardware, and some out of band management messages or telemetry messages to kind of augment that would be at least an avenue I think we should look like that.
Regarding the limitations with things like snapshots, I mean, have any of the research or lab setups you've seen use what they call aggregation taps, where you basically have passive taps on all the fibers, then you feed the mirror copy into a switch, and then it can inject a hardware timestamp and then feed it out of band as like a PCAP file?
Oh, okay. Yeah.
Have you seen those in any of the academics? I mean, I know we use those in finance specifically, but I don't know if we're one of the only major users, probably us and maybe cybersecurity.
Yeah, I don't think that they use them for this because I think the majority of the work that people do or kind of they just kind of do a theoretical analysis or
Gotcha.
one model or another, put it in a lab, and typically they take one or two existing kind of old protocol that already exist and do that. So I don't know if it's chicken or egg. If it is because you can't you don't have any access to tools like that that will allow you, as you say, like something where you take a passive fiber and spit out almost a PCAP file where you could trace every packet and how
Exactly.
that would be. But I don't know if the lack of that tool is what prevent them from doing that or other reasons. But it doesn't seem like a lot of the work that's being done has a thorough analysis of competing scenarios or even from the deployment. So some people were complaining that they try to basically deploy certain quote unquote improvement, but they did them stepwise and they introduced them in some stuff. And a lot of the analysis that people did in the models only assumed that the everything kind of changed at the same time, which even in a lab environment, that doesn't happen that way. So as the two different versions of that algorithm were running in parallel, all hell broke loose. So things didn't work very well. So I think for it, if the tendency of, for a lot of these application, people are going to have a transport application with the choice of different congestion mechanism, then a proper diagnostic and monitoring tool or tools will be quite useful. The second part is basically kind of the network metrics as well in terms of kind of feeding. So there was an attempt at, I think there was a lot of different people trying to kind of have a coherent way of feeding network metric to congestion control. But I think once you move congestion control to an application layer or to a transport / application layer that lives in user space, it might be a good time to revisit that and then see, for example, if you have a congestion algorithm where you can have it as a module and you can tailor it to basically one usage or another. And if all the congestion algorithm have access to whatever signals are provided by the underlying infrastructure, then that could be also something that would be useful, I think. So anyway, so
Question.
I'll stop here and let.
Yeah, I have a question. So most of these congestion control algorithms are reactive. In other words, there's a problem, let me react to it. Are there any proactive congestion controls out there?
There are. There are, and however, they haven't been as successful. I don't know.
I mean, one way to maybe answer that question is, if what we mean by proactive is kind of, I have an idea what my flows are. Like I know what's going to fill the pipe, and therefore I want to kind of plan my traffic so that the pipe doesn't get full. That in a shorthand, that's the description of TSN. That's essentially what the whole family of TSN protocols do. Is if that's what we mean by proactive, yeah, there's a lot of stuff out there that's proactive in that sense. And so, in other words, to me, those family of protocols don't even use congestion control. They sort of work to avoid congestion by sort of planning ahead for like what the flows are going to be. I think in most data center applications, you don't know what the flows are going to be, so they can't do it that way. Yeah, you know, they can't be proactive because they don't have enough information to be proactive. I don't know if maybe my assumption is wrong there, but
no, actually, you're on to kind of so. It's a question of scale. So, for example, if you're doing, for example, a radio over Ethernet and running it over TSN or something like that, and you have long-lived flows with specific characteristic, you can schedule them ahead of time. So really the question between where you are and what Dan was going is a question of scale. As things kind of scrunch down to a small scale and things get really dynamic and a burst comes alive and goes there. So people have attempted to basically do scheduling at a, let's say at a smaller time step. And you can do it in a kind of, there are a few algorithms, I can't remember the names. I've seen so many acronyms over the last couple of months, but you can basically do some scheduling. Some of them even have a central scheduler, but kind of getting something where you could actually predict or not basically have an understanding of where the other nodes are and kind of puts packets across is actually quite is something that people are looking into. There's people who are looking at some like really weird cases that I don't want to get into the weeds and into some of these details, but that is definitely something that can be done. I think the reason I spend a lot more time on the reactive side is because probably kind of getting to something that that we can do with precise time with a reactive that is kind of, you know, the next step, say in terms of precision, let bat, swift, and then go to the nanosecond accuracy. We can do that in a fairly reasonable time. The scheduling part of it is definitely for Dan and Hisham. That's I think it's a little more involved thing, which would probably, if there's people on the call where there's some either a student or researcher who want to kind of tackle some of those problems, I think there'll be some interesting avenues there, but it would be a little harder and longer to do than say the reactive algorithm.
If I'm understanding you, Med, I mean, sort of your recommendation is kind of let's take a smaller step with the time-based congestion protocols as opposed to a larger step like proactive ideas. Am I understanding you right?
Correct. Actually, yeah. I would say that I would see that I was hoping that basically we would get into like almost a sequence of things. So start with basically something like diagnostic and telemetry and doing characterization is something as like a, you know, in David's world, they do it all the time. So how could we bring that to congestion? So that is a very small step. That is something that is kind of can be done in
gotcha.
time. Then next one is providing a reactive. We'll have to do some analysis in terms of are we going to go sender, receiver, a combo of both, etc. Is it going to use exclusively delays? Is it going to be delays augmented with whatever else whatever metrics we have, etc. And then see what those fit in. And then the last layer would be basically the scheduling part, which would be the I would say the kind of the holy grail, the ultimate goal. But in at least this is my opinion, in my mind, like the first two steps are a lot kind of more reliable to take those smaller steps and increase the scope as we go.
Makes sense to me. Yeah.
Has there been any work looking at actually applying a dollar cost sort of based method for doing this? So people can actually price in, especially if you have multiple parties, multiple teams, multiple systems of what is the value of getting a certain packet with a certain reaction time?
Not that I have seen. I don't know if anybody else.
It's something we had floated in finance. The idea being if like 100 people all want to get their packet to a certain gateway, actually have them offer up money to get there to basically buy queue priority in the switch. But I would think you could even do that internally within organizations and then get people aware of what is the cost of particular hardware sitting idle versus not.
That's funny. This really brings back memories, David. We talked about this scheme kind of half jokingly in an IETF meeting, like in 1999. It was like, if we could have some sort of dynamic cooperative congestion management capability where we can do these kind of asks and bids. You might be able to have some sort of value-based exchange for that. Yeah. But we weren't thinking in terms of money at that time. At that time, we were thinking in terms of like exchanging flows or that kind of thing. But yeah, but it's funny. It brings back memories. Good question.
It can be also round robin, like when you get a turn, then you go back in the queue. So, I mean, it really depends. There's so many different schemes.
Do all these schemes rely on the clients being positive? What happens if you have a client who goes in and says, I want to take as much bandwidth as I can.
Yeah.
And if I see congestion starting, I'm going to start flooding information out because I know the other guys will slow down.
Yeah, it has to be on good faith.
So-
that was actually a concrete problem, low level. People would implement their own TCP stacks, and then they basically would ignore whatever's being advertised in terms of the available space to increase the odds of getting your packet, and will just wire rate, essentially denial of service it. And this is one of those areas where things get very messy. People aren't used to dealing with custom TCP offload engines.
Are you talking about Spotify?
No, I'm talking about in financial markets where you have like $1 billion on the line.
Well, everybody wants to be first there.
Exactly.
So this is a great segue into, so maybe you guys also have some thought on this. So there was a discussion about basically what you are mentioning, David, and I think Hank alluded to that, is they try to kind of define the rule of engagement into this. If you're rolling your own, should we establish you need to be as nice as a TCP? So what is that baseline and how is that baseline defined? And I take it back to basically characterization and diagnostic, where what constitutes a well-behaved flow node user is so kind of subjective. We don't have
one second.
Sorry, is someone?
No, good. I don't know.
Yeah, so it is a subjective thing so far. We don't have the tools and not the contract, but at least some guidelines in terms of okay, if this is going to be the Wild West where everyone is going to roll their own, how do we define, like we're sharing resources? Do we just go in there and the switch decides, okay, I've seen enough, I'm just going to drop? So do we go back to that? And so I'm curious as to see how people feel about it. So there was actually calls for basically defining what you need to be TCP friendly, meaning at worst you need to behave like TCP cubic or whatever. You pick your favorite. But other people argued that it's kind of almost an arbitrary setup where you go like it needs to behave like this. Network change all the time. How do we find the new good behavior? So I don't know. I'll leave the floor and maybe other people want to chime
Just one thought. I would be curious if one of the reasons this problem existed and people haven't there's two different use cases, right? One is where you're dealing with external parties, so you don't know what they're going to do. The other is you have your own data center for, let's say, doing like grid computing or LLMs. You actually do have complete control over the network. In that case, I would think you could actually do very, very tight synchronization. The caveat to that is historically, it was very difficult to know at a user mode level when you call send, when are those bytes actually going down the wire because of all the different buffers. But there are a lot of techniques now where you can severely lock that down if you do things like kernel bypass, even have exclusive control of the NIC itself. I would think that may be the enabling factor that would allow you to do this really at scale potentially. And then it's almost sort of like what we do with job batch scheduling, but you do it at a much tighter granularity of when to read data. And then potentially there could even be cases where you can use things like multicast to then optimize it. So you're sending the same data to multiple parties versus sort of the traditional, just, fire up a massive grid and have them request whenever they do.
Right.
Do we have a sense for the people working in this field, how much of the effort is specifically on dealing with external parties, more like a Google serving web pages versus on the internal data center side of the infrastructure?
Almost. So I have to qualify it. So when I went and picked up, 25 surveys, looked at the stuff that they got, ended up with about 220 papers.
Mm-hmm.
I would say, like a very odd sampling of this thing. 90% is completely controlled environment.
Gotcha.
So the majority of people are not looking to build the next TCP. Almost every paper, or almost all of them, start with, we have a network that looks like this.
Mm-hmm.
We tried whatever, DCQCN or one of the algorithms that is in there. Here is what our application. So some of them are like just one application, and some of them have 2 or 3 kind of like-minded applications that they are running, HPC or ML or distributed computing, and they see something completely go haywire, and they usually go and kind of try to study it, figure out what the application is doing, what the algorithm is doing. And if you took like whatever algorithm you pick, and then you go into the sequence, the kind of the timeline, how each application, each refinement, the interesting thing is like people kind of put a new stable point for a given thing, and then they create a new unstable point for somebody else.
Exactly.
So that's why I was joking about the rebuttal to the rebuttal to the rebuttal. So it's a hard problem. So, it's as you change the application and the requirement and the speed, it changes a lot of things. And with the limitation is like a lot of people are dealing with timers of a certain. So people were tripped by things like timer was set hardwired in the NIC to be this much. And they just bumped into something where the NIC was going crazy and timing out things. And so sometimes you can, like, no matter how much you change the algorithm, you're not going to get out of your troubles. So
very interesting. Are there any solutions discussed where they abandon IP and UDP entirely and just do everything raw Ethernet?
So actually, quite a few. So when I was talking about Quick and how they piggybacked on, so that's kind of basically, it seems to be like the template for getting your new whatever you want to do in this domain. You start with doing a software solution with the UDP IP and just use off-the-shelf stuff. Don't spend too much time trying to kind of, and once you get it, if you have the means and the money to actually do your own NIC, and even like if you're like quote unquote slingshot or something like that, and you want to kind of optimize down to the wire, really whatever you know algorithm or kind of, if you have an addressing at that level, you can totally skip everything else. If so, if for example you come up with a scenario where you have a self-contained fabric and you have a scheduler,
Mhm.
and you don't need any of the other stuff. It's like, why?
Exactly.
Like
Yep.
you can do it. It's not adding anything to you. Now, to kind of basically jumpstart your development, it would be extremely difficult for you to start that with that as a as step one. It's probably
Why is that? Because doing raw Ethernet now is fairly well supported.
Oh, sorry, you meant that kind of going over raw Ethernet. No,
Yeah, exactly. So,
this
so
one-
go ahead.
for this one, for this one, people are even skipping Ethernet. They're
Yeah.
going straight into, like, they'll put something in the preamble or whatever.
Yep.
And they'll have basically a kind of a source-based routing. So you don't even use the kind of the MAC addresses for
Basically raw
Yeah.
SerDes at that point, and you can line it up with like photonic switches. And
Correct. Yeah. It's but agreed. If you want to do it over Ethernet and you have some way of resolving addresses at the application layer, absolutely, it would be no different than piggybacking on UDP.
but is that an area the academics have worked on at all yet? I'm just saying we're going to do a protocol, we'll do it raw Ethernet. Forgot about IP. Forgot about UDP.
Haven't seen too many of those.
Okay, interesting.
Not sure if it's due to availability of labs that most of them actually have labs at their universities that are already set up.
Gotcha.
And basically it comes with the tools and everything. So it seems like once you look at a few of the comparison, you kind of see the natural progression of all these work and how they go into kind of the same sequence of events.
Gotcha. And for most of this work, does it assume that the switches are sort of provided as is by the vendors, or are they also looking at sort of custom switch architectures as well?
Actually, you get kind of a bifurcation in there. People
Mhm.
are kind of looking more into like the network telemetry. They either go into something like a P4 enabled switch,
Mhm.
or even some of them kind of the brave ones go and implement some switch fabric based on FPGA platforms or
Exactly,
something like that. But typically, those are actually trying to get into algorithms that focus on switch support.
Mhm.
So if your view of the world is congestion can only be solved by having the switch participate, that's and then you have the other camp, which is basically we don't care what, and we don't want to know about as long as you give us this tiny bit of information and it's well structured, we will deal with it end to end. So it seems like there is, and of course the in between. So you get.
Yeah. Med is kind of a comment on that. I think the answer to your question is kind of reinventing the Ethernet PHY and the Ethernet MAC. To me, doesn't have a lot of value in the sense that there's only so much you could squeeze, so much benefit you could squeeze by kind of trying to redo that stuff. Like even Tesla, who is sort of the king of invent your own thing, kind of stuff. I mean, for their TTP protocol, they reused the Ethernet PHY and frame, right? Because, even by their own claim, they were like, well, we didn't see any distinct advantage of kind of going down that level. And, it's good enough because the Ethernet frame is, pretty atomic, and so they just built, of course, they built all of their own stuff on top of that, which is, people do and is fine. But yeah, even they reused it. To me, if they reused it, that's kind of a sign a lot of people are going to reuse it. But, I don't know.
Yeah, absolutely, I agree there. Like the absolute majority of people are using that, and actually, it doesn't seem that like even UDP IP, kind of to David's comment, it doesn't seem like a lot of people are kind of looking to even skip that portion. So I know I've seen like, I mean, again, it's not a good statistic. Is like what Med picked up from the stuff, but there was maybe 3-4 papers out of 200 that I've seen where people said, "Well, we're gonna do away with the UDP IP layer." So I mean, take it for what it's worth. But for the random sample I made, that was kind of the rate of people that even kind of went into the optimization of actually going through directly to Ethernet framing rather than writing over a UDP IP.
So, Matt, it's not really a question. In one of your slides, you mentioned a contribution by Paul Patroff about this source of law. If you go back to your slides.
Sorry, what slide, Hisham?
So there is a slide where you mentioned, you recited a contribution from Paul Patroff. Paul Patroff.
I think that was the ECN stuff. Yeah.
But I can't find it. That is the one. I can't find it.
I'll send it to you.
Send it to me. Good.
Yeah. So this was part. So this was. So he has actually a pretty interesting. I know Hisham, you were interested in this stuff, but I put in the backup here. He had a nice kind of comparison between PFC, DCQC, and SFC, and what they were trying to do. So I'll send you after the call. I'll send you.
That will be great, because Paul Congdon and others, we started together a congestion isolation project, because the BFC problems like head of line blocking and other things. So, and Paul Congdon was leading this project, and it was congestion isolation. The source flow stuff came later, but I wanted to really, but maybe after the call, Ahmed, I want to get your perspective on the congestion isolation, which is a standard now, has been specified. That's the last thing, really. I did it when I was working with the Nanjing team in China, So, but the source of flow stuff happened later, and I don't really know what happened there. I'm glad you mentioned it. But maybe offline.
Absolutely, yeah. We'll talk about it, because I'm interested as well. So you said actually it's a finished standard. Honestly, I didn't have time to kind of go over the whole.
No problem, Matt. So the congestion isolation, we finished it. It's a specification now, but the also stuff is still going. But that happened later, But I wanted to get your perspective on the congestion isolation.
Okay.
Because between you and me, although I have done it with the Nanjing team, I'm not fully convinced that it is the best solution, and I haven't seen so far any market traction for it. But I appreciate your perspective, Matt, on it.
So I'd be interested in the group if anyone has any feelings in terms of or inklings in terms of do you think that the kind of the direction in terms of going after something like congestion with precise timing? So is this, do you feel like it's a worthwhile direction, or something that we should dig in more deeply in it? And as I said in the beginning, I'm kind of biased because this is kind of in a little bit in my wheelhouse. But as they say, like someone with a hammer, everything look like a nail. So I don't want to be so in tune with that thing to kind of. I'd like to, if there is people who actually don't believe that that's gonna, I would love to hear from them.
Okay, so Matt, you and I know each other very well, so this is a conversation.
So you're not going to be nice to me, is that it?
No, I want to be enlightening. So I'm well known for someone who is, perhaps immorally attending these meetings because I don't believe in precise time, but it's actually a very subtle and interesting problem, and most people who are not trained in physics aren't aware of something called a measurement problem. But let me take this right back to someone that was said a moment ago. It was declared that Ethernet was pretty atomic. That is untrue. In fact, it's so untrue that it's a blind spot that almost every network engineer has. And so what a Ethernet is in the new Ethernet 2025 program, it means atomic Ethernet.
Before we argue over this, though, we should be clear that different people may be using the term atomic in different constructs. So let's just specify, what do we mean by that?
Yeah, maybe define that first, and then Paul, just
I mean, all I meant by it is it's a small enough unit that it's useful. You don't need to tweak it anymore. That's all I meant by it.
Sort of like digital logic, right? We just sort of accept it and use it. We could do this analog, but
let's see, Paul, is that the definition?
No, I'm not going to accept anyone else's definition now. This is a much longer conversation. I don't intend to
Can you give a reference at least, because people who watch this?
I will be dealing with this in my very first presentation on Tuesday morning at the Chiplet Summit in the Ethernet 2025 workshop. This is exactly the issue I'm going to point out. And I'm in conversation right now with all the original founders of the Ethernet, including Robert Garner and Bob Metcalf and several other people. And oh, by the way, Paul Condon is coming to the workshop.
Really?
Yes, he's coming to the workshop on Tuesday. Yes.
That's excellent.
I don't intend to prescribe before I diagnose. And so my job isn't to be the purveyor of information, is to be the curator of ideas. So that's my job. Next Tuesday morning, I invite everyone to come to the Chiplet Summit. Email me if you would like a free ticket for the entire Chiplet Summit. I've got a number I can give out to people. But the basic central issue here is that Ethernet is not atomic. And I cannot give you this in a soundbite. It doesn't work that way. You have to unlearn something first before you can learn how to make Ethernet atomic. Anyway, I think I've said enough. Med, are you up for the challenge?
Unfortunately, I can't be in next week, but hopefully next time you have the Chip Summit, I'll be there in person.
Paul, why don't you add also some virtual presence so Med can be there as well?
Well, I'd like to, but this is really a kind of an unconference style where we're putting together different working groups that are going to go to different parts of the room, and there's even tables and chairs being set up because right now we look like we're in danger of overflowing the room.
Yeah, but let's just have also a Zoom call in parallel.
Okay, this is what I'm going to do. This is a big issue, and how do we run a new standards organization, produce specifications quickly? We have an OCP approved project. That what we're going to do is the very next week in this time slot, we are going to be talking about how we solve this problem, but mostly from a collection of all of the inputs that we've had from everyone. The goal is to take the n-squared objections to modifying Ethernet to connect them down into a linear order that everyone will agree on, and then vote on the top 3 to 5 themes that we should be working on. I do not want to preempt or presuppose how that is going to turn out. People who are at the workshop, and David's going to be there, Kevin's going to be there, and I hope many of the rest of you will be there. But this will be something that unfolds. I don't have a prescription to solve every problem you have. What we do have is an opening, a forum, a way of having these discussions that we should have had a long time ago.
Yeah, wonderful.
Paul Congdon now is working with Ultra Ethernet Consortium.
I'm acutely aware of that, but the Ultra Ethernet Consortium is a switch and router consortium. They are purveyors of bandwidth. They do not know how to sell anything else but bandwidth. And what we're selling is different. It's reliability and ultra low latency.
But he's not coming to represent.
No, no one's representing anything. Anyone who shows up, by the way, don't worry about, someone claiming that you're, supporting this. We will never say that. Come, work with us, argue against us, listen to probably one of the most creative unfoldings of technical knowledge that you will see, at least this year.
And have fun.
Yeah, Paul is a great guy. I like him a lot.
Yes.
But just so you know, there's an entire activity going on behind the scenes yet, which I can't announce. But most of you know that I was the founder of the Storage Networking Industry Association, so I have done this before. I was also a vice president for standards for the IEEE Computer Society and on the and a big shot on the IEEE Standards Board. I find the IEEE way too slow to do anything interesting. So here's what's going to happen. I'm going to be the czar of this. Rule number 1, no excuses. If you're not attending the meetings, then you don't accumulate voting points. Number 2, no whining, because what we're going to do is make progress really fast. We're going to make progress daily. We're going to meet weekly, and we're going to produce a specification in months rather than years. Well, by the way, rule number 3, have fun.
Yes. All right.
Med, as a quick thing to answer your question, no opposition. I would love to talk to you about this stuff. It sounds great.
Hisham, you wanna put the last rule and we close the call.
No, I want rule number 4, free food.
All right.
We can provide that. Yes. Send me an email and I will get you a free pass, which includes food.
Thank you, my friend. You're fantastic.
All right. All right. Everyone.
You're coming. You are
sorry?
coming.
Yes, I hope so. Yes, yes.
Thanks, everyone. Great presentation. Yeah.
Thank you, everyone.
Thank you,
Thank you,
so
Ben.
next,
Really
in 2 weeks, next in line, we have Jack from Stack. So he's going to give us a presentation about what Stack is and how we can work with them.
This
All
is
right?
Stack on the finance side, right?
That's right.
Excellent.
AC.
Glad to hear you guys connected.
Yes. All right. See you guys later. Bye-bye.
Take care, everyone.
Take care.
Always a pleasure.
Bye.